Let's say we wanted to add some scaling to this. Well, we kind of already did some scaling with the xd and yd. We're scaling these two vectors to get the original length of vector that we wanted to rotate. And what we could do if we wanted to scale this resulting vector as part of our transformation of our point, or our sprite, for example, if we wanted to rotate and scale the sprite, we could modify this xd and yd value that we use in this equation here. Just before this, we could have added this xd times equals scale, yd times equals scale, if we want to do it like that. And then this will be the scaled version. So if our vector, we wanted it twice as long, because the component vectors are twice as long, the resulting vector will be twice as long. Normally when we do 2D, we use sprite batch and it kind of sets everything up for us. But if we want to create our own batcher, or we want to create our own camera system or orthographic view, we can do it ourselves too. And typically we want the origin, the 0, 0 in the top left corner. If we want to do it like OpenGL usually has it, it'd be in the bottom left corner. And we got our width and our height that we want our screen at. The 0, 0 origin is by default in the center of the camera. So we're going to need to create a projection matrix which will provide us with the version of everything where it's within the coordinate region that we want it in this sort of format. So basically what we have normally in the device, we'll have all our polygons or quads. In this case, since we're doing 2D, they're going to be quads that'll be facing directly towards the camera. And we're just going to drop the z coordinate and just focus on the x and y coordinates. So in the device, we'll want those to be between -1 and +1 in the x and y directions, so that the center of the camera is essentially 0, 0. And even in 2D, there's still depth values that can be stored for each sprite, and those can range from 0 to 1 for us. If we're doing OpenGL, normally that would range from, I believe, +1 being close and -1 being in the distance. For us, it's going to be ranging from 0 to 1 and 1 being in the distance. One thing to make a mental note of is this width is 2 units wide, and this will be 2 units high. So essentially, we have x is -1, x is +1, and same in the y direction. Depending on which way you have your y-axis flipped, this could be -1, that could be +1. So y would be +1 and -1 down here. And this is kind of what we want our coordinates to be put into. We want to put them into this space where it goes from -1 to +1 in these directions. So it's kind of normalized to this space for the device so that it knows what to do. And here at this close point, this would be 0, and this would be +1. However, like I said, if this is OpenGL, this would be -1, and this would actually come back further, and it would be +1 over here, if I'm not mistaken. How do we get our two-dimensional images into this sort of normalized space? To do that, we create a projection matrix, orthographic projection matrix. So what we have is our screen that we want, which is the right side minus the left side. And the left we want at 0, the right we want at 1024. Should be a width of 1024. And we want to go bottom minus top, which would be 768. And if we wanted 1024 width to be normalized to 1, like if we're normalizing for a render target, we'd divide it by 1024, and that would give us 1. Same with bottom minus top, we'd divide by 768 to give us a distance of 1. So whatever the coordinate is, dividing it by that number will give you, if it was in the middle, for example, it would give you 0.5. So what we want to do is we want it to be a distance of 2 instead of 1. So we'll take, instead of going 1 divided by 1024, we're going to go 2 divided by that. So the hardware likes to use matrices to do transformations on the vertices to get them to where they should be and how they should look. I'm not going to go too much into how matrices work, but I can show you how to set them up, sort of, or what it's doing when you call the function to set it up. So first of all, I've got this identity matrix here. If I want to scale the x, y, and z by a certain amount, so in this case, we got a distance of 2 that we want divided up into 1024 units. So what I would do is go 2 divided by right minus left, or we could just say width. I'll say right minus left, and then we wanted to scale on the y, so we do the same thing to that. I'm just going to show the final matrix here. Realize I have a little bit of a mix-up here. So the top, we actually want this to be -1. We want this to map to -1, and we want that mapped to +1. So instead of going bottom minus top, as I had said, I was thinking, well, bottom's greater, but we want this to be a negative number. Actually, we want to flip these. This should be top minus bottom, because we want the y point upward to be negative when it's mapped into here. So negative 2 minus f minus n, I'm pretty sure that's actually correct. You'll notice these are going to map to, or scale to be between 0 and 2. And we want to transform it so that 0 is in the middle, so it'll actually be between negative 1 and positive 1. To do that, we can use this column here to add our translation. Now keep in mind, if you're in direct 3D, for example, because the way it maps the columns and everything, it's actually the other way, so you'd have the translation down here instead. I'll show that over here after I'm done. Our translation would be, we want to go -1, so -1 here, and actually let's put this in the correct sort of way. So what we should have is translation, basically this identity matrix, and what we want is we want the negative of left plus right divided by 2 to get the middle, right? And we want to do the same for the negative top plus bottom. Sorry if this is really messy. Negative top plus bottom divided by 2, and negative of far plus near divided by 2. And when we multiply these two matrices together, it's a very long and extensive operation, but you'll notice the 2 on the bottom is going to cancel out with the 2 on the top here, and then you should have this L plus R on the top, L minus R on the bottom, and you kind of do the same thing for the other two also. So I'll just put those in here following that rule. So what we should end up with, okay, so as I wrote here, it might be hard to read, translation to center. So this column here is doing the translation to get it so that instead of being over here at 0 to 2, it's moving everything so that it's -1 to +1, and 0, 0 will be in the center. So through that matrix multiplication, we would have canceled out the 2, and we would have ended up with the r plus L over r minus L, once you sort this all out, with the negative in front of all of it. And same with the top and bottom, it's t plus b over t minus b. And keep in mind that our bottom is a higher number than the top, so it ends up translating in the other direction, which is what we want, because we want this top to be -1 and the bottom to be +1. And you'll notice here too, for the x here, if the left is 0, then it's basically just r over r, which is 1, and this becomes -1, which is what we want. We want it to move it back -1 so that the left edge is here. And so we do the same sort of thing with the far plus near over far minus near with a negative in front here, and that'll translate everything so that this cube is around 0, 0, 0. I'll quickly write to what the DirectX or Direct 3D version would be, and instead of -1 to +1 for this cuboid thing, it should be 0 to +1, I believe. Okay, so the only difference with the DirectX one is you'll notice that we put our translations over here instead, and we changed this to a +1 instead of a -2. And I think that's correct. You might want to double check that, but that's the idea behind setting up the orthographic matrices. So just a quick review of what that does. This will change the x component to be scaled, so it's 0 to 2. So the horizontal coordinates will all be scaled along here so that it'll fit within 2, which is why we divide by r minus L, 2 divided by r minus L. And then it'll be 0 to 2 at first, but then we have this translation on the end. So this stuff here essentially scales the x, y, and z axes of this x-axis, the y-axis, and the z-axis. And then this stuff here all ends up getting multiplied by 1 and tagged onto the end of each one of these as translation. This will probably end up being -1, so that'll move our 0 to 2 to become -1 to +2, and the same idea for the top to bottom and the far to near, so that everything's within the cuboid that the hardware is expecting. Any data outside of that cuboid, beyond our far or near planes or any of the sides, that stuff will be ignored by the hardware. Or I should say, it just won't be rendered because there's no way it'd be visible on the screen. Now, if you wanted to set up an orthographic matrix so that instead of it going from 0 to 1, it went the other way to go into the depth, so that it's like it is normally like in OpenGL, for example. You could actually set the far and near to be negative values and make the far like a farther negative value, for example. And that should work. So you could go, for example, negative 0.1 to negative 10, for example, or negative 100, or negative 1,000, or negative 10,000. Just depends on what you need. So I set up this little project. I called it mybatcher, and I added the input class that we made before. You don't have to necessarily use that, but it just used the keyboard and the old keyboard state and get whether the key is pressed or not by checking if it was pressed, and if it is pressed now, then we know it was just pressed. And also we got one for checking to see if the key is down. It's essentially all we really need from that. And then down here I got that escape method in there too, so that if the person pushes escape, we can just check that and it'll exit. In the update loop too, I should probably put input.update just to make sure that it's getting those key states. We're probably going to make a batcher, and just for testing I added a couple of textures. I got some source rectangle information here. You can use whatever you want, create whatever textures you want, whatever source rectangles would be valid for your project. So all I really did here, I'm just kind of showing what I was doing so you know that you're not missing anything. I set up the rectangle coordinates to extract from. I could just briefly show you what images I used. So, for example, I got this background, I have a boss robot, I got a spaceship, some explosions, some thruster fire, and some laser fire. Let's see, I got a far back. Oh yeah, I got a mid background too that I can use additive blending with. And these are just for setting up the animated explosion and flame. These are the source coordinates. It's just loading them here. And right now, just clearing the device. If we want, we could set some custom graphics parameters here. If we want to be able to index or use indices that have a very high range, we could use high def, or we could just stick to high compatibility and use reach. For depth format, we'll use, say, depth 24, and I'm using 1024 by 768. You can use whatever settings you like. Go over to the right here, I've already done it, but you can right click and go add a class, and I've added this quad.cs. I started off by saying I'm going to have an effect, default effects, so whoever's using this quad batcher doesn't have to supply an effect, but they can bypass either the pixel shader, vertex shader, or whatever they want, anytime they feel like. It's going to hold a reference to the graphics device, and that'll just make things a little handier. And we're going to use a dynamic vertex buffer rather than a static vertex buffer. And that'll allow us to create, on the fly, we'll be able to create a huge batch of vertices and then draw them all at once in a single draw call. So there's not a lot of device, I should say all the device updates and anything that we want to send on the bus to the hardware can all be done at once, so that'll minimize any kind of delays between frames. So yeah, this will hold all our vertices until we're ready to toss them into the vertex buffer. And the vertex buffer is really what carries them onto the hardware. It has to be a locked section of memory. So when we write to the vertex buffer, we gotta lock it or map to it and then unlock it, and then that memory can't be tampered with when it's trying to update the graphics card with the data. The indices right here, I mean, we could even make them local to the constructor. They're not going to change. The quads will consist of the same triangles. We're just going to be changing where the vertices are located and what colors are assigned to those vertices. So the index buffer just controls the vertex order for drawing, and we can tell the graphics card to draw however many triangles we want. So if we want to specify 2 quads, we tell it to draw 4 triangles. And the index buffer will already be set up, so we'll just give it the span of what we want it to draw. So if, for example, on our sprite sheet, we had this tree and maybe some grass here, maybe some flowers, and let's say we just wanted to draw this here. We need to supply texture coordinates that range between 0 for the left side of the texture and 1 for the right side of the texture. So this might be at, say, 0.6. horizontally. And then vertically it might be like 0.4 or something to 1.0 if this was the bottom, or if this is the bottom, I should say. That's a terrible picture I drew, but actually let's say we want to draw the tree. So we'd supply the texture coordinates for the corners using the source rect, and we'd have to divide up. So sorry if I'm explaining this poorly, but if the texture, say 1,000 wide, then we'd have to say 1 divided by 1,000 is our multiplier, and then whatever texture coordinate we want to extract from, so say it's like right here at this position, maybe we just want this little patch here, it has a little ladybug in it or something, we would take this coordinate, which might be 100 or something, so we'd take 100 and we multiply it by the 1 divided by 1,000. So we'd multiply it by, and we could call that m, for example. So we'd multiply it by m, which is the multiplier, and that would probably give us 0.1 into the texture, so that's between 0 and 1. And the graphics card will be okay with that value, so it'll be able to extract using those UV coordinates, those texture coordinates. So if we wanted to draw this flower with this quad as a sprite, we'd send a source rect that it would convert to those texture coordinates, and then it would have to supply those texture coordinates for each of the 2 triangles that make up this quad, because all the quads are actually made out of 2 triangles. So you may be familiar with a lot of this already. And since we're using a clockwise order, we'll be culling counterclockwise triangles. Since we're drawing sprites that face directly towards the camera, we don't actually care whether they're culled or not. So we can tell that you don't need to do a dot product to test to see if it's facing away from the camera or not. You can just go ahead and draw it, no matter which way it's facing. I don't believe it draws the front side and then the back side. That wouldn't make any sense. So this would be index 0, this would be index 1, index 2, index 3, and to draw these 2, I would draw 0, 1, 2, and then that would be a clockwise winding order, and it would know automatically that that's what we're after if I just give it 0, 1, and 2. And then for the other one, using a clockwise winding order, I can give it 2, 3, and 0. And that'll give us the second triangle. And with each one of those, I'll need to give it the corresponding texture coordinates, as well as where on the screen those are, and our matrix will convert that to the proper -1 to +1 space in the graphics card. So I prefer not to store a list of textures and just sort of, and not have to sort textures before drawing. So what I would prefer to do actually is tell in the begin which texture it is that I'd like to deal with, and then just extract all of the sprites I need to draw off of the same texture map, which is called a sprite map. So all of the images are all on one texture, and if we do need to change, we can just start another begin-end pair. So the texture that I would use with this quad batcher, I'm just going to call it text. We can send it once and just keep it in there, and then after we call end, if we need to draw something else, we can start another begin-end pair. So normally when you're dealing with vertices, quads, triangles, polygons, or 3D objects, you do what's called a local transform. So if I wanted to transform these coordinates locally, this would be, say, -5, this would be +5, 0 would be in the center. It wouldn't actually be at this location, it would be like this. So then you do your local transforms, rotate, or scale first, and then, oops, I guess it doesn't really matter if you rotate or scale first. You'd scale first, then rotate, and then translate to where it is. Ideally, you should scale first. And then you do the world transform, which puts it where you want it. Now, since we're supplying particular points on a screen, these positions in a sprite, they're not going to be local coordinates, they're going to be world coordinates. We'd have to first specify an origin or a center to the sprite of where it is on the screen when we do our draw call. And what it'll do is we could apply a matrix transform, or in this case, since it's 2D, it's very easy for us to just apply a vector transform, it's essentially the same thing, and vector transform it to here, so that all these points are around 0. So we've subtracted that origin from each of these points to make a version of these numbers that would be around 0. Then we can apply a rotation. Oops. This is what would happen if we didn't do that first. Just as an example of what I'm talking about. If we tried to do a rotation first, this is what would happen. because the rotations always happen around 0. So that is why we subtract that origin to get those points at 0, wherever 0 might be. Then we rotate it around the origin and scale it. So I guess we'd scale it first, rotate it around the origin, and then translate it back to where we actually wanted it. Now, if this is a 3D model, you'd probably only be storing the local coordinates with the origin as 0. And like I said, this would be -5 or something. That would be +5 on this side. You could get away with just rotating it because in memory, it already has this centered around 0. It's not in some sort of screen coordinates to begin with. So then you translate it using a world matrix to translate it to where you want. The world matrix, you could also have it so that it scales it or does other things to it too. As I had kind of mentioned before, if we apply that same rotation that we showed in the first tutorial from the side view between these two vectors, pretending that this is the x vector instead of this one, and we're using the same y vector, what we can do is we can apply a rotation this way. And in effect, it's almost like if we were changing the y radius here, whereas the x radius is staying the same. It's similar to that. Basically, all we're doing is we're swapping the x and the z and doing it from the side view. And what we're going to do when we get to the end of all that is we're just going to take the x and the y coordinates after all of the results are added together. And the matrix can combine all of those results for us in one single operation. So before we were doing the z-axis rotation, and what I'm talking about now is the x-axis rotation, and we can also add on the y-axis rotation, which would rotate these around this way, around this circle. Now, hypothetically, if these are all length 1, you could actually use this basis of vectors and multiply by any x, y, or z amount against these bases, and what that'll do, it would be almost like you're stacking together a certain number of horizontal vectors of these, and a certain amount of vertical vectors of these, and a certain number of z vectors. So you'd take one of these, go to here, but if you want it to be twice as long, then you multiply it by 2. If you want it to be 3 times as long, so that sort of idea where you're basically just taking these 3 vectors and multiplying them by a length to get how far into each one of these directions those coordinates go to get your end resulting vector and your end point. So that's kind of how the rotation transformation is working with the matrices. It's kind of tricky to explain it in a way that's easy to understand, but if you look at the first tutorial, you might get the idea. For this tutorial, actually, you can probably forget about that. We're probably only going to work with taking where we want our sprite on the screen, these coordinates that we supplied, and subtracting that origin, that center point, to get these points here, and rotating them, and multiplying the radius by a scale amount, moving them back by the origin amount, back to where we wanted it, and adding on some translation offset. So basically when we draw our quads, we got 0, 1, and 2 going clockwise. Now, say this was the 5th triangle, or the 5th quad, I should say. We might be working on vertex number 20, starting right here. So then this would be 21, this would be 22, and that would be 23. So we just need to do the transforms and rotations and such for those 4 vertices and add them to our vertex list for all the quads that we've created so far that we're going to draw all at once when we're done. And the index buffer is static, meaning it doesn't change, meaning that the indices always just count upwards. So like for example, for the 5th quad, it would have went through, so there's 6 indices per quad. So it'd be up to index 30, for example. So 30, 31, 32, 33, 34, 35. And all the index is doing is telling it which vertex to select out of the vertex list. So we've got 1, 2, 3, and 4, 5, and 6 for the first one, for example. So as we add these vertices, we're also going to count the number of vertices and put that in a variable called vertex count, or vert count. And to get the number of triangles we want to count in our end for when we're done creating our batch, we'll just say triangle count is equal to vertex count divided by 2. Because as you can see in a quad, there are 4 vertices, but there are 2 triangles. So if you divide it by 2, you get the triangle count. Now the indices don't change, so when we call our draw user indexed primitives, we can just pass it indices, and we don't have to set the index buffer because it's already been set. the vertices that we're passing in are the ones that we're actually creating on the fly here, these ones. To put the vertices into the vertex buffer so that everything's kind of locked in memory and ready to be transferred through the bus to the graphics card uninterrupted, we use this vertex buffer.setData, and that can grab these and put them on there. Actually, you know what I realized here? Normally you'd have to set the vertex or set the data into the vertex buffer using this, and then set it to use this vertex buffer. In this case, we don't actually have to do this. So I'll just go here. So we can get rid of that. And the reason is we're using draw user indexed primitives rather than just draw indexed primitives. So here we're specifying user index primitives, and we're passing in the vertex list that we created. So this step is actually unnecessary if we do it this way. And so we can set a shader to take effect, and we pass to it the world view projection matrix. And I'll show you more about the world view projection matrix, how we set it up, and how the shader that we are going to associate with this batcher, how it's going to use this world view projection matrix. It's essentially just the projection part, the orthographic projection part, that's actually going to do anything. In this case, normally the world matrix stays as an identity matrix, which means it won't do anything. Same with the view matrix. So we don't even really need to calculate these each frame, unless we're doing something really special, in which case we might do something weird with the view, or we might adjust the world matrix to create a screen shake, or if we're doing a different type of camera panning method, we could actually just modify the world matrix. So here I'm showing that if we wanted to, we could allow passing in custom effects, and here I'm calling it effects. And it may contain a pixel shader or a vertex shader or both, and whatever is applied here, it's just going to replace either the pixel shader or the vertex shader, or both, depending on what it's replacing, from what was applied here. So we might want to keep the vertex shader from this and apply our own custom effect, which contains a pixel shader, and when we apply it, it'll replace the pixel shader that it's going to use. Here I'm saying device.textures 0 is equal to texture. That's whatever texture we set to use with this particular batch. If we wanted, we could actually, it's actually probably safer to write that line as this, especially if you're using more than one texture. You would write it as, and you want to make sure this name matches. So, for example, this might say sprite texture inside our shader, or the texture might just read texture. And then in that case, we'd want to pass it the texture itself. So we can call this draw user indexed primitives. And here we specify the format of the vertex, so the vertex declaration. And in this case, we want position, color, and texture coordinates. So the texture coordinates is where it's going to extract it from on the sprite sheet. And those have to be specified in 0 to 1 space. So I'll show you how to set that up from the source rect and convert it to 0 to 1 coordinates. I'd also like to be able to specify color, so we can colorize the texture. And if we wanted, we can create custom draw methods that allow us to specify red, green, or yellow, or any color we want for each vertex individually, and it'll do a nice smooth blend of color between those vertices. Obviously, we also want the position of each vertex. So all of this stuff is going to happen all at once. Any of the device changes would go here, and it'll all be inside the end call. So when we use the end method, we're going to set all our device changes at once, set any applicable textures for our effect in here, set what shaders we want to use. Obviously, we'd have to do that first. And, oh yeah, just a note too. This line we might want to put here instead, because if we pass this transform, it's going to pass it for the vertex shader here. But then if we change which effect we're applying, I don't think that this will get into this effect. So this actually should be here. So just make sure that make a note of that. Any of your effects applications have to come first. Then we can set our parameters. And when we're done that end batch, we can probably set vert count to be 0, or if we wanted, we could set vert count optionally to be 0 when we call begin. Before I continue, I thought it might be important if I just make sure that people understand the concepts of what normals usually refer to. And in 3D, when people say normals of a 3D model, what they're actually often referring to is the direction, the 90-degree perpendicular direction away from the camera. So essentially, if you pretend that this is the top of a surface here,
of some 3D model, you have these what we call surface normals, and the surface normal is the direction the polygon is facing. It's that 90-degree perpendicular direction away from the polygon, and it's a normal because it's been normalized to a length of 1. So all of these have to be a length of 1, and the reason for that is we want to be able to do dot product calculations against those. That's a special type of product where if you use a dot product of one vector that's also a length of 1. So if I had this light coming in and I wanted to find out how bright it should be, so I'd want to know the distance, or I guess the angular magnitude between this vector and this vector. And you can use the dot product to figure out how intense the light should be at the point that the sampler is sampling at. So in the pixel shader, fragment shader, it would figure out how different are these two vectors. When the two vectors are lined up, that's going to be a maximum value 1 because they're very much the same. And if they're perpendicular, that's going to be considered 0 in either direction. And so it's going to get no added light, or very little added light. If it's negative, then you know it's facing away from the camera and should be excluded from the calculation. And in fact, if it's negative, the hardware will automatically cull it. However, you can still have a negative value under certain circumstances because the vertices themselves actually are what's going to hold the normals. And typically, unless you're using smoothing groups, the vertices hold an average of this surface normal and this surface normal, and that gives you a smoother look. If you want really sharp edges, you'd have to use separate vertices at this same point so that you can have a vertex with that normal and a vertex with this normal to get a sharp edge. So that's where smoothing groups come in, and that's something you do in your modeling process. Now, obviously the vector of the light to the surface is not one that you can use because it's facing the wrong way, so you'd have to use the inverted vector, which is this. So you just have to negate the x, y, and z value of the vector, or just negate the vector itself, vec equals negative vec, to get the vector pointing up away from the surface, towards the camera, and or towards the light source. So that's getting into some 3D stuff. This isn't really a tutorial about 3D, but I thought I'd at least make you familiar with that. And the reason it's going to be important for us to understand that with our sprites is when people talk about normals, they're usually referring to these vertex normals rather than the surface normals. And the surface normals are calculated in the shader from each pixel or fragment by blending or interpolating sort of an average based on how far it is. So if it's 20% in, it would be 20% this one, and 80% this one, and 20% this one. So it's interpolating across the surface and using your pixel shader to determine how it should do the calculations as it goes. I'm kind of sidetracking a bit here, but what I want people to understand is when we say normals, oftentimes we're referring to vertex normals and not specifying vertex normals or not specifying surface normals. In our case, when we talk about normals, we're just talking about what it actually refers to, which is a vector of length 1. And we may not necessarily be talking about vertex normals or surface normals. So those two can get confused because people just usually say normal for short. They don't say surface normal or vertex normal. So when we make vectors, we can normalize it to a length of 1, but also if you have something that's within a space that's of some width and some, I'll put the W here, if we're in a space that's of some width and some height, and we have, say, these texture coordinates in here, and we want to normalize it to be a 0 to 1 float value for the width and a 0 to 1. The reason you do that is because the hardware is making its calculations on the basis that it's extracting from some percentage within your texture map. So if this is, say, 0.1 to the right, then it's 10% into the texture, and that's where it starts extracting the UV data. And it maybe here it ends at 0.35, which is like 35% into the texture. Our texture coordinates, though, normally aren't between 0 and 1. To get it into the texture coordinates, we have to take our U value. So normally, when we refer to texture coordinates, we don't say W or H or X or Y. We refer to this as the U coordinate, and the vertical ones we refer to as the V coordinate. So So the u coordinate is going to be equal to this width, the original texture map's width, divided, well, I should say 1, which is how wide we want it, so 1 divided by the texture's width. That would give us a multiplier. So we can take any coordinate in here, including 1, like if this is 1, and we multiply this by the width, you can see if I multiply this by the width value, that's width over width, which gives us 1. And if I multiply this value by, say this is 1,000 wide, if it's 1,000 wide and I multiply it by, say, 900, if it's here and it's 900, then this should give us 0.9, and 0.9 is 90% between 0 and 1. So it'll give us 90% into the UV space where it's going to extract from the texture. So that's kind of how it's doing it in the hardware. So we got to set up our UV coordinates to work with that. And what we're going to do is we're going to create a multiplier that we can just reuse in our quad class that'll convert, and that's that 1 over width or 1 over height depending. We're going to use that as a multiplier that we can multiply against any value that'll give us the corresponding coordinates. So when you see scale u or scale v, that's that multiplier that does that conversion. We could also say that it's normalizing the coordinates, making it between 0 and 1. So it can get confusing because normalize or normal can refer to multiple different things, but it basically refers to something of a length 1 or in a space that is acceptable to the hardware. But most of the time when we refer to normals, we're just referring to a vector that has been changed into a unit vector of length 1, and that's useful because we can scale it to whatever length we want and it'll keep pointing in that same direction.